Okay, thank you very much for the introduction. Let's start with easy calculations. We have last class we explored the electric field, no? So we have positive charge, punctual charge. Normally in physics you analyze particles, no? You analyze, even when you analyze the dynamic of Newton, you remember you analyze the motion of a car, you assume the car is a particle. It's not accurate because, well, in most of the cases it's accurate. But what happens if the car starts to turn or do many strange things, then it's not accurate anymore. No, you have to take into account that motion also, that rotational motion. But in most of the cases, the approximation of particles is good enough. Even when an object is extended, for example, I have this right here, an object of this dimension, and I charge it with a charge Q. If I am far away, I can assume that this is approximately a particle, and the electric field lines will be approximately radial anyway. So it depends where you're located. Do you remember the electric field lines go to which direction in this case? They go outside or they enter? By convention, outside. They go outside. So it's radially outside. And remember the electric field as a vector decrease inversely proportional to the distance. This is a unit vector, radial. So if you far away, this electric field tends to zero, obviously, because the radius will become large. This becomes small. If I put a particle, let's put a test particle here. I will call it Q0. The charge of this is Q, and the distance between both is 5 meters. And then I ask you, okay, the charge of this guy is 1 coulomb, and this charge is the charge of the electron, let's put, which is 10 to the minus 19 coulombs, I think, of that order of magnitude. Then I ask you, okay, calculate the force that this charge feels due to the presence of this other charge. This charge has to be much smaller than this for not distorting the electric field, no? This is not the same case of the dipole, because in the dipole, both charges have more or less the same order of magnitude. Then how will you do it that? What do you think? Any opinion? First, calculate the electric field here, no? In this point. If I calculate the electric field, let's calculate the magnitude because we know it's radial. Then, of course, the magnitude of this electric field will be the constant K. This is 1 coulomb divided 5 meters squared. Yeah. If I introduce the K, which is in the textbooks, normally in this kind of problems, I give you the information. Or if I don't give you the information, I just ask you to express the response in terms of the constants or variables. Then at the end of the day, this is K divided 25 in the corresponding units. Let's say this is in coulombians, this is the, and the constant K is appropriate such that this is Newton divided by coulomb. Okay, and we know that the force, magnitude of the force is just the charge, the test multiplied by the magnitude of the electric field. It will be the charge of the electron, the norm, the magnitude. Why I put magnitude? Because the charge of the electron is naturally negative. Then, of course, this particle is positively charged. I am trying to emphasize that it's positively charged. If I don't put these norms, I am telling to everybody, the charge is negative, and that's not the idea. Then, can somebody tell me how can I charge an object in that way? How can you charge positively an object? If what is the carriers which move are negative, actually. The electrons are usually the carriers of electricity, I mean the guys who move, Of course, there are exceptions. You can have ions which can be positively charged or negative, and they can also be carriers of current in the fluids, for example. If you throw salt to the water, actually the water, pure water is not a good transmitter of electricity. It's when it has impurities where it can transmit the electricity. Well, normally the water spread will be not pure, no? So you have many particles which have many ions which help you to transmit the electricity, and that's why many people die in that way. Hopefully not us, no? But let's say it has happened, this kind of accidents have happened. So in the case of here, coming back to this problem, before for replying this question, normally, of course, when you touch a surface and you apply friction, some of the surface release electrons. Of course, if the electrons escape, that object is charged positively. Is that you have this eraser, and some electrons escape from here. This becomes positive because it lost negative charges. That's more or less the idea. So now, if we apply the magnitude of the force, then will be this multiplied by A, and A we calculated already K to the 25 divided 25. Yeah, this is the force. Now let's explain something here. Look at the expression in general. If I write the whole expression, the magnitude of the force will be K Q0 divided distance squared. Well, the norm of a unitary vector is 1. This is precisely the column law. And this resembles more or less the Newtonian gravitational law of gravity. Remember that in the past, when people saw this coincidence, immediately they say, oh, there must be, these two interactions must be unified somewhere. Maybe it's true, they might be unified somewhere, but by the day, we don't know how to unify gravity with the other interactions. We have so far unified the weak interaction with the electromagnetism. It's called the electroweak theory. It's very successful. It could predict particles, predict the bosons C and W. Stephen Weinberg got the Nobel Prize. It was the most famous. Weinberg, Salang, and Glasgow, they shared the Nobel Prize. They did predictions incredible. Interestingly, in that theory, they assumed that the neutrino is massless, and the neutrino came out to be massive now. We know it has mass, so we don't know what's the mechanism of giving mass of the neutrino. But coming back to the point is, they unify these two interactions with the strong interaction, which is QCD, basically. We have the grand unified theories. But nobody knows how to incorporate gravity there. And one of the problems is because gravity is classical. We don't know how to quantize it. We don't know how to make a quantum theory of gravity. We have semi-classical approaches like Hawking radiation. Hawking radiation is semi-classical approach. Semi-classical means you use classical arguments mixed with quantum arguments, and then you get some results and some approximations, but it doesn't mean that they are completely accurate. The fact that black holes evaporate particles is a quantum effect, for example. And we have candidates of theories of quantum gravity, but nobody can claim that we can quantize gravity yet. So that's why we have not yet unified these guys. I spread these problems because, I mean, some of you might be curious, and in future, you never know if you are encouraged to explore. Some of you will not be encouraged, of course, but some of you might be encouraged to try to solve these important problems, because this is what makes science exciting, knowing what are the problems, knowing that not everything is written, that nothing is absolute, that all the theories are approximations to reality, but they can fail into some regimes. Look at Newtonian gravitational law, which fails when the gravitational field is strong, or when there's some dynamics, no? So what in mind by the times of Newton was a tremendous success. We couldn't explain several things. We will go back to this part when we explore relativity in future sessions. So this is the way to calculate. Now, let's keep this charge positively charged. I will delete this. Anyway, Later on, you can check in the video. Let's keep this charge one column. And now I put a negative one. Let's put the negative one in red, minus Q here. Obviously, this is a negative charge, so the lines of electric field, they enter or they go out. They enter, of course. They enter. And of course, together, these guys form a dipole. So technically, all the lines which this guy spread goes to this one. Why? Because they have the same magnitude of charge. However, if I duplicate the charge here, only half of the lines starting from this source go here, and the other half goes to infinity, radially to the infinity. If I multiply this by 3, the charge, 2/3 of these lines will go to the infinity, and 1/3 will go here, etc., etc. This could be a question in the exam. Now, I want to calculate the force between two guys. It will be exactly the same as we did before, but let's add one more charge. Let's add a third charge here, Q0. And then what happens if I ask you, what is the force that this charge feels due to the presence of these two guys? Then this is an interesting question. And
if we're considering the Cartesian coordinates, and it will only feel it in the y-axis.
Exactly, you have to decompose in x and y, no? Let's analyze. This is where the vectors, the vectorial character of the force is important. No? For example, if I go to here, obviously I need to know the distance between these 2 points and the distance between these 2 points. I can give it to you later, but let's assume that it's arbitrary initially. Then since this is positive and this is positive, naturally this charge repels this one. So this charge will feel a force in this direction due to the presence of these guys. Then let's call this force FQ, Q0 is the force in this direction with some angle. This force will have the tendency to attract because they have opposite sign. No? Then it will be a force in this direction. Let's call this for F Q0 minus Q. So what do you notice? The effective force will point in which direction? To the right-hand side, no? Right-hand side, you look at the screen, this direction. Direction will be the effective force. Sometimes in the test, I will ask you only these kind of questions in which direction the effective force goes, because the calculation sometimes is trivial, sometimes you will have to calculate. Here we have applied something very important. It's called superposition principle. If I put any amount of charges, the total force or the total electric field in one point will be the superposition of all the contributions, individual contributions of each charge. But why I can do that? There is a strong reason in gravity I cannot do that, for example. In the Newtonian limit, yes, but in general relativity, no. And there is a strong reason for that. And this reason, of course, in the high school, nobody will tell you that. Somebody can guess? Say something, say whatever, invent. With McDonald's. I know you cannot talk at this moment. Go on. Well, the number of particles, well, not exactly. That's not the main reason. I think the main reason, I am sure of that. The main reason is that the theory is linear. Let's say electromagnetism is a linear theory, and gravity is a non-linear theory. And this is a consequence of the fact that the carriers, let's say the carriers of the interactions are photons, and the photons, they don't have charge, so they don't interact each other at the lowest level. Of course, if you take into account quantum arguments, the vacuum generate particles and these kind of things, there are bubbles, Feynman diagrams, etc., which you are not yet at the level of understanding those things. There will be a tiny non-linearity contribution somewhere, but those are quantum effects. But at the classical level, the theory is linear. Then, for example, when these two guys are interacting, they exchange photons. Remember, the photon is a massless particle moving at the speed of light. There is another photon here. There's a bunch, millions, and not millions, maybe billions, trillions, whatever photons exchange. But these two guys, they don't feel each other classically. Because this guy, the charge of the photon is zero and the charge of the other photon is zero. They don't feel each other. So in that sense, that's why the superposition principle can be applied. The theory is linear. If these guys interacted, you cannot apply this superposition principle that easy, at least not in some regimes, which is what happened in gravity. The carrier of gravity is what? The graviton. And the graviton has energy, but the energy is equivalent to mass. So it's a source of gravity. So the gravitons interact each other, especially when they have high energy. So that's the difference between gravity and this thing. So these are the facts. I mean, these are the concepts I like the students to learn. I think this is even more important than doing the calculation because this is what gives you a different view of physics, different vision, developing the intuition. No? You have a question. I think I can see your face.
No, it's just is graviton the carrier of mass, or is mass is the graviton the carrier of mass, or is or gravity is a consequence of mass? Something.
That's a good question because actually Einstein, this is the paradox of Einstein gravity, no? Einstein gravity, you have a geometric size on the left-hand side and the source term, no? The source terms, they form the geometry, but the geometry tells to the bodies how to move. So I think in this nonlinear scenario, it's a good question, what is the source of gravity, no? Because the gravitons themselves are also source of gravity.
Its gravitons are theoretical, right?
Theoretical right now, yes, but everything points in that direction. Let's say, I mean, if you want to quantize, let's assume all the quantum theories, let's enumerate them. Electroweak, they have carriers, bosons C and W. The W bosons are charged, the C boson is neutral. And the photon, no? The photon, which is the carrier of the electromagnetism. And we have in QCD, we have the gluons. The gluons, which also interact each other. They have charge, called color. That's why the theory is called chronodynamics. Okay. So if we analyze all the theories, the pattern is that all interactions, they need a propagator. Let's say they need some particle or some, well, I don't want to call it objects, but they need some particles, fundamental particles, which carry the interaction. And if we are intended to quantize gravity, it's naturally to think that the graviton is the guy. Now, another thing for believing in gravitons is, I remember I was in a conference in China, in mainland China, a few years ago. Many famous guys were there, actually, I remember. And there was a guy, I forgot, I think he was Spanish or I don't know. By then, the gravitational waves have not been discovered yet by LIGO. But we have the evidence in 1974, no? The Holst-Taylor, the famous Holst-Taylor, events is there were some binary objects. They rotate around each other, the pulsars, and they approach to each other at some rate. And the rate of decreasing match with the energy they have to emit via gravitational waves. The calculations, the observation match, giving this, the masses, giving all the variables. But we couldn't measure, we couldn't detect gravitational waves directly. This was an indirect evidence. We knew that, but we didn't detect in gravitational waves yet until 2015. But by the time this guy was skeptical, I remember he said, no, gravitational waves don't exist. That's bull something. And then I was thinking, bull what? And, and I was telling him the same response I am saying now. If you calculate the Wickfeld approximation of general relativity, you obtain an equation of a spin 2, which is the equation of the graviton. It's something like, I will write here just, this is a parenthesis, no? This is not part of it. This is the D'Alembertian is like the nabla operator, but in space-time. It's second derivative, but it has a minus and plus. No, minus for time, plus for space. H mu in some gauge, because we have to fix some gauge, is equal something like minus 16 G P and a source, some kind of source here. S mu nu or T mu nu or whatever. I think it's S mu nu. S mu nu is T mu nu minus 1/2 G mu nu T. T is energy momentum tensor. This is where the source terms appear. Now they have the charges, no, masses, flow of energy, and pressure. And then when we see this equation, this is the equation of gravitational waves, and the discovery of gravitational waves, these calculations match with what is observed. No? All the LIGO events have matched with this. So this is the first step pointing to the direction that the gravitons must be real, because gravitational waves themselves are theoretically a bunch of gravitons propagating through space-time. Then it's natural to believe, but now, because science is more demanding than what people imagine, it's not only writing whatever and people believe you are, oh yeah, you're amazing. No, is you write something, you predict something, but that thing has to be measured, which is something that many scientists have forgotten. Many scientists do many Marvel and Doctor Strange theories nowadays, but I mean, at the end, you say, how do you measure this thing? I mean, we have to worry a little bit about how to falsify these theories. But detecting a single graviton, I mean, think for a moment, gravity is the weakest force. It's the weakest force. I believe personally, my first paper in gravitational waves was in 2008. I wrote a paper with my supervisor, Marino Wakowski in Colombia. He's a German guy, actually, but he was working in Colombia at the University of Los Andes. And we wrote a paper about gravitational waves where we explained the effects of dark energy and so on. But by the time I believe it that they will not detect directly the gravitational waves, because when you see the amplitudes are so small, but these guys, they found the way amazing. It's quite amazing how they could do it. Now, at this point, personally, I believe in my lifetime, they will not be able to detect a single graviton boat. Never say never, because these experimentalists are also clever. Now they are working hard, they are trying to find a way. So theoretically, of course, it's a hypothetical particle, but I think all the logic, all the directions point that there must be true.
Do all particles with mass emit?
Yeah, because mass is a source of gravity. Mass is a source of gravity, not only mass, energy also. Even the equivalence mass energy, exactly, which is a consequence of special relativity. And that's why the universe accelerates. Actually, that's very important, because when we discovered in 1998, actually, it was discovered that the universe expands faster, faster, and faster. The most serious candidate going out to be the biggest suspicious guy is dark energy, which is vacuum energy. And why? Because the energy and mass are equivalent, and then the energy is a source of gravity. That's the main reason. So, okay, all these comments came out just because I was explaining why the theory is linear. No? Coming back to electricity and magnetism, electromagnetism is a linear theory propagated by carriers which don't interact with each other. That makes the theory linear. Actually, this explanation is not even mine. This is from Richard Feynman. Richard Feynman was the guy who best explained physics in this world in the 80s, probably. And in his lectures, he explained why how a theory is linear when it's not linear based on these ideas which I am sharing to you right now. The famous Feynman lectures in physics, which are in textbooks nowadays and so on. People took notes. Then, okay, now we know there is a superposition principle. We can apply it safely here, not in gravity, unless we were in the Newtonian limit. In the Newtonian limit, still we can apply the superposition. If I ask you this question in an exam, for example, I just close the door because I feel people talking there. I have to give you the distance between these two guys. I have to give you this distance. Let's call it 5 meters. Between these two guys, 5 meters. And then it became basically a problem of geometry at the end. I have to give you also this angle and this angle. Let's assume that it's 45 degrees. 45 degrees. Then, of course, you will have two forces pointing to the right-hand side with the same magnitude. And in the vertical axis, those forces cancel. So I can ask you in which direction this particle will move. To the right, because it's in non-equilibrium, unless you are keeping it with something. No? You put something to keep it on the board, fixed. So now this is a basic example, Coulomb law, etc. Let's now analyze the Gauss law. You remember how to calculate? There are 3 major geometries, which we explored last time in the last class. Of course, volunteers can come if you want, if you are not shy with the camera. But if you are shy, it's okay, I will understand. There are concerns about privacy, that my face cannot appear in somewhere, then I also understand. Let's put it this way. Let's start with the spherical symmetry. Simple charge, 2 problems. I will mention 2 problems. The first problem is this. Charge Q. Simple. The second problem are completely different. No? I will put first here. And the second problem, I will put spheres. A solid sphere, charge Q, a hole here, like hollow air in Converse with Godzilla. And then this guy here, I'll put minus Q here with some density. Let's call uniform density. Density of charge per unit of volume, no, uniform. Let's call this rho. And this also rho. Of course, with the corresponding sign, no? And this is a hole for this part. Then I will apply the Gauss law for predicting what is the electric field in different regions. Let's start here with the first problem. I will delete this number because it's confused. Remember, Gauss law is it comes from the Maxwell equations. But let's go step by step. If I paint a surface here, imaginary surface, what is the flow, the total flow, the net flow of electric field here? It's not surrounding the charge. 0. Because the number of lines which enter are the same number of lines which go out. So this is what the Gauss law told us. The Gauss law tells us that the closed integration of the electric field dot product, the area, differential area, is the integration in the volume, density of charge, volume divided epsilon 0. If the density is uniform, this is charge, the charge enclosed, different divided epsilon 0. This is more generally, this is the divergence theorem, actually. The divergence theorem, because one of the Maxwell equations is telling us that the divergence in the electric field is density of charge divided epsilon 0. The divergence in the volume is the integral in the surface. This is a mathematical general property. So if I integrate the integral in the volume of the divergence of a field is equal to the, let's write here, is equal to this, basically, to this. These two things are equivalent. Yeah. Well, you will not learn this part. I mean, this is unnecessary. I'm just telling to you for those who are curious. The part what you really need is this part. This is the part you need. Well, you need to know from where it comes, because later when we see the Maxwell equations will require this form, differential equations, which will come out to be the equation of a wave propagating at the speed of light. And this is how the magic of physics. I mean, this constant epsilon zero and the constant mu zero coming from magnetism, they join in a single term, which comes out to be the speed of light. So I mean, things which are completely different can join in a single theory and define a new constant, a new invariant, which was the speed of light in vacuum by the time. So even by the time, what Maxwell did, what these guys did was tremendous, even before Einstein. For example, this was before Einstein. Of course, Einstein had all the glory and so on, but let's say if you start to analyze, many guys did huge contributions also. We cannot underestimate those. Then now, I will delete this surface here.
What is the symbol behind the energy?
What?
The symbol behind the E?
This.
Behind the E, yeah.
Divergence. This is the Nabla operator. Like when I do this, I will just write here for illustration. In X, Y, and Z, for example, this will be X, the component X, the component Y, the component Z. Why? Because this is like doing the block product of this. The X, I direction, the Y, in the J direction, the Z in the K direction, dot product, the electric field X, Y, Z. This normally is not learned in high school. Normally you don't learn this, not even in university sometimes, unless you study physics. But I am just telling you this as an additional information. Obviously in the exam, I will not ask you about this or not. I just want you to know, to understand how is the process of discover things. Then let's delete this because we are going to solve now the problem. Which problem we solve? I want to find the electric field in this point by using the the Gauss law. I say Gauss law? Yeah, Gauss law. Then I have to paint an imaginary sphere here. Imaginary sphere which has a radius arbitrary r. It has to be symmetric. The surface can be arbitrary and the Gauss law is applied, is valid. But I have to be smart. If I want to solve the electric field, I have to be smart and use the symmetry of the problem. So let me delete this part here because this was additional information which we don't need right now. I will delete this part for not confusing you. And then let's focus. Let's focus here. Then, of course, the closed charge of this surface is just Q epsilon zero. Now, since I painted a sphere, I want to develop this integration. Along the surface of the sphere, the electric field is the same in magnitude. Because remember, the electric field just changes with the distance, not with the angle. The angle doesn't matter. So in other words, the electric field here, the magnitude is the same electric field here. In magnitude, the same electric field here. in magnitude. That's it. Bingo. What does it mean? Do you remember the definition of dot product from your school, from something? This will be the norm of the electric field times the norm multiplied by the cosine of the angle between both. No? The vector area also points radially outside. The vector area, if I apply the differential area here, this vector also points in the same direction. So they form a zero angle. Cosine of 0 is 1. No? So at the end of the day, what I can do is just, this will come out to be the electric field, the magnitude, multiplied by the area of the surface. And the area of the surface is 4 pi r squared. 4 pi r squared is equal to this. Then at the end of the day, I can solve the electric field, the magnitude, and the 4 pi comes down. What does it look like? Coulomb law. Only that k, the constant k, is 1 divided 4 pi epsilon 0. Yeah, solve it, bingo. So we can prove, this proves that the Gauss law is consistent with the spherical symmetry. Excellent. Now let's apply something more complicated for the same geometry, I mean spherically symmetric. This is more complicated because this is a solid sphere inside, this is a hole, and this is partially solid sphere, I mean with some solid part, but it's hollow inside. So inside this hole, the hole of this sphere, this is a smaller sphere and a hole. And I want to calculate the electric field in different regions. Let's put this radius 1. To this radius, let's call it radius 2. And to this one, let's call radius 3. Then I want to calculate the electric field here for different regions. When the radius is smaller or equal than radius 1, when the radius is between radius 1 and radius 2, and when the radius is between radius 2, radius 3, and when the radius is larger than radius 3. So in other words, I will calculate the electric field here, 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 and outside. Outside, I can tell you immediately what's the result. I don't need to do the one outside. Somebody can tell me why? How can I know that outside, what is the result? Immediately, I don't need to do the calculation. Look at this. The internal charge, I almost say in Spanish, carga. The internal charge is Q, total charge Q. The total charge of this guy is minus Q. Exactly. So all the electric field lines of this guy will go to this guy here inside. So at the end, outside, there will not be electric field. You will not feel anything. It's 0. And really, I know the electric field here. For radius larger than R3, the electric field is 0. That part, I don't have to do it. It's different, of course, if I duplicate this charge inside, the problem will be reduced to this one. For outside, only that you have to apply the superposition principle. You have to assume this charge, remind that is 2Q, minus Q will be Q. It will be exactly the same problem. You will obtain exactly the same result as a board for outside the body. Inside the body, the thing is more turbulent. And take into account that I am assuming uniform density. This is a huge simplification because if I assume that the density change with the radius or with the angle or whatever, the things get more complicated. No? Normally in the textbooks in university, they put densities changing with the radius, but not with the angle. I don't remember a problem where that possibility is open. But we will be simple here. I will always put uniform density because what I care here is that you know the concept. I don't care you to solve complicated problems or these kind of things, but I care you is to develop the intuition here. You will develop the intuition. So let's do this problem. I will delete this one because we already saw it and it's recorded. So you can check the video after. So let's delete here. Let's delete this. Let's put the problem more to this side. Here in this area. Then let's go for radius smaller or equal to the first radius, which is this inside. What can I do in that case? Let's apply Gauss' law. For applying Gauss' law, I need to paint an imaginary surface. What kind of surface do you think I should paint? A spherical symmetry? I paint a sphere. Where? Inside, because they're asking me inside. Inside this radius, I will paint that. Let's isolate this part inside. Let's put the charge here. Let's put it here. This is the sphere. It has total charge Q, uniform density, and radius R1. Like this. Let's paint the Gaussian surface. Gaussian surface. The Gaussian surface has an arbitrary radius. I will put the radius R here. R. Then let's apply the Gauss law over this guy. What is the Gauss law? What can you write here? Guys, pay attention because this will appear in the exam. This kind of problem, no? For sure, this kind of problems. Gauss law, for sure, I will ask this one. So it will be, let's apply the Gauss law again. Let's write the equation. Integral the surface over the surface imaginary is the charge the surface enclosed divided epsilon 0. But the charge with the surface enclosed is the integral of the density, which is uniform, multiplied by the volume, which you enclose. And on the left-hand side, you have electric field 4 pi r squared. Like this. Uniform density, I can put it outside the integral. What is the volume of that of a sphere? Or 3 pi r cubed. No, the volume of a sphere or 3 pi r cubed. If you apply the derivative of this, we become 4 pi r squared dr, which is the area of the surface. No? So at the end of the day, let's put here density 4 3 pi r cubed divided epsilon 0. I am applying the integral over, the volume enclosed by this surface inside. No? So the radius is arbitrary. And if I apply the left-hand side this guy will cancel partially. So at the end, what I obtain, let's write the result here. The electric field in that region will be 4 and 4 cancel, pi and pi cancel. It will be density R 3 epsilon 0. Look at the difference. Now the electric field grows with the distance. But why does it happen? Why do you think the electric field can grow for the distance? We didn't say that the electric field decreases with the inverse of the radius squared a few minutes ago. Then what is happening here? Say whatever you invent. Was McDonald? Okay, great. So any idea? Why is growing now? So I could ask you in the exam, okay, tell me the electric field inside this region. It grows proportional to R. It decreases inversely proportional to R. I can put it in a multiple selection and you have to tell me. But why is proportional to R in this case? The magnitude of the electric field. Exactly, and when you extend this more and more, you are enclosing more and more source. You are covering more charge. if you have more source, naturally, that compensates the decreasing effect. Obviously, the electric field generated by a tiny region here, it will decrease inversely proportional to the R squared. But take into account that you are covering more charge the more you go away. Then naturally, the electric field has to grow. That's what happened. Now, if we go to the second region, this is for the first region, then let's write the result. For this, the electric field is rho R divided 3 epsilon. Now, let me delete this for doing the subsequent region. Let's do the second region is the following. I will isolate here. You have the charge here. And you have this hollow region here. Then this is a hole, right? And then you have the radius here is radius 1, and we call this radius 2. And I want to find the electric field here in this region, so I paint the Gaussian surface here because I am interested in this region. Yeah? And the radius of that Gaussian surface is arbitrary, R. Let's apply the Gauss law again. What is the closed charge in this case? This has uniform density. The closed charge will be Q, total Q, because anyway you are enclosing completely the sphere. So this problem, this result reduced to the previous one, a spherical symmetric point particle. It's having a point particle in the origin, and it decreases inversely proportional to R squared. Let's do it. The Gauss law on the left-hand side, will give you 4 pi R squared. Okay. And the right-hand side is Q divided epsilon 0. Q is the charge enclosed. Then this will be the typical result. The usual one will be electric field Q divided 4 pi epsilon R squared. Nice. Excellent. Excelente. Muito legal, não? Muito legal.
Very Brazilian.
Yeah, Brazilians they say legal, no? Português they say muito bom. Muito bom, não? Tá tudo bem, não? Tudo bem. Okay. And then this is the typical result, but this is only valid in the hole between the radius 1 and radius 2. Inside the radius 1, no. No. Outside the radius 2, no, because you start to enclose another source with negative charge. Now,
only considering that the inner charge is the only one that has influence in that region, right?
Yes. Yes, because anyway, the electric field goes radially outside.
And we're assuming that for the positive and the negative, it just goes outside.
Yeah, because the positive charge emits, and the negative charge just absorbs. Now, and we have to follow the Gauss law. The Gauss law is telling you the total flow of electric field through a surface is equal to the closed charge, the charge enclosed by that surface, divided epsilon 0. And if I surround this, the only enclosed charge is this. I am not enclosing the charge outside. I am enclosing this charge. Then I have to follow the Gauss law. And it works, no? The Gauss law works. And take into account, for example, if I paint the electric field lines here in this diagram, they will come from this positive to this negative. Like this, like this, like this, like this, like this, like this, like this. Perfect. Here is where the electric field starts to die because of but still inside this region, the electric field is not zero. The electric field is zero outside, but inside we have to do the calculation. Then let's write the second result is the trivial one. I will delete this part again. But I will not delete the picture. I will delete the result. I will just say that for radius between R2 and R1, the electric field is proportional to 1 over R squared as usual, or is equal to K Q R squared divided by squared. Usual. Now let's go to the region. Well, I didn't like that this is too close to this because I had to paint the other surface, but I think you will be able to understand. I will just put it like this in blue better. This part, there's another solid area with charge minus Q and density of charge minus rho. Let's put the sign immediately here, minus rho. And I want to calculate now the electric field in this area, in this region. Then I have to put my Gaussian surface here. With an arbitrary radius R. And I am exploring the region between R2 and R3. Between this inner radius here and this external radius here. So remember that this radius is R2, but this one here is R3. If something is not clear, please ask me. Because I know the picture is not the best. I'm not the best artist in the planet. So you can ask me, oh no, it's not clear, then I can clarify to you, but I think it's clear enough. Of course, it had been better to post a picture or something, but these kind of problems are simple to paint anyway. Then what happened, actually before going to the break, because I think I abused from you today, we overpassed the time for the break, but let's close this problem and then we go to the break. Because outside I know the electric field is 0, I don't have to calculate that. Let's calculate this one. Gauss law again, Gauss law, left-hand side. E 4 pi R squared, the same. Right-hand side is what changes. The closed charge is, well, I don't have to put the sign because I know I'm interested in the magnitude. Okay. Or let's say I have to take into account the sign difference between the charges. I am enclosing two charges now. I am enclosing this Q and I am enclosing this, partially this one. Then what is the total closed charge in this case? Will be, let's write in terms of the density better. And let's assume that they have the same density per unit of volume for simplicity. Then we can factorize, no? Then it will be rho divided epsilon 0 multiplied by what? By some volume. Some volumes. Well, there are two volumes here. The first one is the inner one, 40 by R1 squared. This is constant. This is fixed. This is fixed because radius 1 is fixed. Minus 4, 3, pi arbitrary radius. This second radius is arbitrary. This second radius is arbitrary. I could factorize the 4 pi divided 3. I can factorize this. 4 pi divided 3. I factorize here. That is 1 squared, 30 cubed, minus radius cubed. And then 4 and 4 disappear, pi and pi disappear. And then, of course, the electric field will be non-trivially the result, which is rho 1 cube minus R cube, so divided 3 epsilon R squared. This is the result. Of course, when this is equal to R3, this has to be 0. And the reason why it's 0 is because rho multiplied by R1 cube is Q, and rho multiplied by R3 Q is minus Q. That's the reason. Pay attention that this R1 is an information of the problem. I could give you the radius 15 centimeters, whatever. This is arbitrary. This is also arbitrary. So, I mean, the complicated part of applying the Gauss law is to know which radius is fixed and which radius is arbitrary. Always the radius of the arbitrary surface which you construct is arbitrary, because that's the radius, the Gaussian surface, let's call it. All the other surfaces, they have fixed radius. And in this case, we are analyzing, look at the behavior of this electric field. What do you notice? When R grows, it becomes smaller and smaller until it reaches the value 0. Here, because the total enclosed charge is 0. So all side, the electric field will be 0. This is the most complicated problem. The two examples, common examples, will be easy geometries, cylindrical. I will not complicate the things for the other geometries. I will just explain the basics. And the capacitors, the two parallel plates. These are the three geometries you can attack with Gauss law, and then we go to the magnetic forces. I will explain a few problems on magnetic forces. If we cannot finish today the electromagnetism, because still we have to cover electromagnetic waves and a little bit of transformers, induced current, and these kind of things. We will spend a little bit of the next session on that. So now we can go to the break. Now it's 4:41, and let me stop here.